So let's see about the cumulative distribution functions. And in previous lectures, already we have known the PDF means probability density functions. Okay, this is the simple pictures that I have taken from the Wikipedia websites, and easily you can search the cumulative distribution functions or probability density function. Then you can easily got this kind of. Okay. I'm just taking the Gaussian normal probability density functions and probability density functions and cumulative distribution functions only for Gaussian normal distributions. Okay, just I'm taking for this now. I'm discussing about this simple Gaussian normal distributions. Okay, this is the simple probability density function, and this is the CDF cumulative distribution function. So that picture already we have discussed in previous lectures. Now relate these pictures from these pictures. So this is the cumulative distribution function. And now what is the importance of this cumulative distribution functions in the probability theory? Suppose let's take here. Actually, we have seen that for the first three pictures, our mean is equals to 0. Mean is equals to 0. If mean is equals to 0 means in the near point of our mean point, suppose here actually our means, this is our mu point. In this area, in this mean area, means in these regions, we have our most pointer lies in these regions. Okay, just say this thing. Now here, just if you just draw the same line, if you just draw the line x is equals to mu, means for first three cups our mean is equals to mu, that is the suppose mu, this is the our line mu. And just see these things. If I give the point, suppose I am giving you the point, and just see the cumulative distributions graph both in the left sides as well as in the right sides. The curve is symmetric. Just see this thing. First observations is in the first observations is the curve, the CDF is symmetric with respect to mu, with respect to the mean mu. This is the first observations. Now the second observations is, if you just plot what is the importance of the, means if I is saying you the probability of, if I seeing you the probability of the random variable, suppose this is the random variable and this is the single observations of the random variable x that's less than is equals to or point mu, this means 0.5. Now let's see these things. Here is actual our mu, here is our actual mu, and see the left side of the mu that lies on the half point. Just see this picture, just compare side by side. This is our mu, this is our mu. In the left side of the mu we have 50% of the point, and also right side of the mu we have 50% of the same things also here. So if for the random variable x, if this is the random variable x, if this is the random variable x, and for this random variable, if probability of the random variable x that less than is equals to mu, so its probability will be 0.5. Just say this thing. Here the point is 0.5. So this is the 0. This is the 0.5. Now I think you have understand, and it will be better. Suppose let's take anyone give and simple anyone give and distribution functions of a. Second thing is, suppose let's take anyone give a distribution functions of a data set. Suppose let's take anyone give the distribution functions n of sample mean is equals to 0 and standard deviation is equals to 0.2. Anyone suppose give these distributions. These data sets are follows these normal distributions with mean 0 and standard deviation is equals to 0.2. Anyone give this data, then we can easily conclude this data. Without visualizing the data sets, we can easily conclude that for this data that the probability of an experiment with respect to that data is then is equals to 0 is equals to 0.5. Okay, we can easily tell these things. Now the second thing is, suppose our distribution is 0.5. Now I am taking our point. Now I am taking our point like that. Here, suppose 0.8. Suppose I am taking here this point. Suppose we are taking here this point. 0.8 to 0.2 means this one, this curve. I am taking the blue curve. Suppose here, suppose like that here, like that here means mu is equals to 0, here 0, this is 1, and between 0 and 1. Suppose let's take 0.4. So 0.4. So 0.4. So from this data set we can easily conclude that if x less than is equals to 0.4, then we can see that this probability will be what? How much point we have actually acquired in this range? In this range, the less than this point, if a random variable less than this, so the point is 0.8. The probability will be 0.8. Okay, means our 80% of the point lies on these regions. That is less if our x less than 0.4. We have only acquired 80% of the random variable. That's the actual importance of the community distributions. We can easily calculate the probability, means how much points our distributions fund acquired on this range. We can easily conclude these things. We can easily find its probability. This is the main importance of the cumulative distribution function. I think from these examples you have understands its importance. Suppose now let's see these things, and now let's just see the another example. Suppose here on the first examples that has given in these pictures. So here the first three curves means blue curve, red curve, and yellow curve. Just see the first three curves: blue, red, and blue curve, red curve, and yellow curve. In this curve, the mean is 0. Just see and compare these things and from the right pictures, left picture and right pictures, compare side by side. Just compare the PDF and CDF side by side. So just mean is 0. Just first from the first three curve mean is 0, but second curve means green curve, the mean is -2. Just say this thing. Here mean is 0, here mean is 0, here mean is -2, and with respect to our means we have seen that with respect to our means our distribution functions acquire 50% of the point, and another 50% of the point is the right side, and another 50% are the left sides. Just see, these 50% on the left side, then these 50% on the right side, these 50% on the left side, these 50% on the right side. Okay, now what is the importance of the standard deviations here? Just see now the compare here from the blue to yellow. First, in blue lines our standard deviations is 0.2, in red line our standard deviations is 1, in yellow line our standard deviations is 5. So the blue line, from the blue line standard deviations is 0.2. okay, if we just increase the value of the standard deviations, then the curve is will move towards the will move further away from the mean lines. Just see this. I'm taking here to understand in green color. Just our first in for the deep blue, just see the deep blue line. In deep blue lines our from the mean the distance is the hit, This distance is this one, and now you increase the standard deviations 1. Now see the distance. We have increased the distance. Now our standard deviation 5. Now see the distance from the mu, green line. So as we increasing the value of the standard deviations, our CDF functions will move further and further away from the mean. Is the third observation. So our third observation is, if we increase the sigma square value, then the cumulative distributions function, then the CDF will move far away from the mean. This is the third observations that we have. So as we increase the value of the standard deviations, our cumulative distribution functions will be flatter and flatter. And as we taken the less standard deviations, our cumulative CDF functions will be much bigger around our mean. See these things. That's the thing in third comparisons. I think you have understand. You have understand the concept. So around our mean. So the first thing is the cumulative distribution functions are symmetric around our mean. That means the probability of the random variable x less than is equals to mean is equals to 0.5. The second observation is, from this cumulative distribution functions, we can easily conclude its probability, means we can easily conclude that how much points our PDF have acquired on this range. We can easily conclude. Okay? And the third thing is, as our standard deviations increases, our cumulative distribution functions must move flatter and flatter, means it will move away from our mean, mean. Now another important thing is the 68. The another important concept on this standard deviation, on this Gaussian normal distributions, is the 68, 95 and 99.99 rule. Now let's see actually what is this rule are talking about. What is the rule? Actually, what is this rule? So this rule is that if anyone tell you the distributions, if anyone tell you the your data set are normally distributed, then easily we can conclude from this rule set of rules, we can easily conclude some properties of this data set. Suppose let's take, I think it will be better if we just discuss this theorem through an example. Suppose let's take, we have a random variable x, and that follows that normal distributions with mean 0, and suppose let's take standard deviations 4, means here our sigma is equals to 2, sigma square is equals to 4, standard deviation is equals to 4, sorry, variance is equals to 4, and standard deviations now will be 2. Okay, that's anyone give this data. I don't know about anything of the data, just anyone by some observation, some from calculations, they are give that data. Now we can easily conclude that using this, if you just see this thing, if our data sets are obeying these normal distributions, then we can easily conclude that our from this thing, and mean is 0. Actually this one is our mean, these things are mean, and here 1 sigma means here sigma is equals to 2, this point will be 2, this point will be minus 2. Then from this theorem we can easily conclude that our 34.1% of the data will lie between mean and the first standard deviations. These standard deviations are called the first standard deviation. First standard deviation. This standard deviation is called the first standard deviation. So now from these distributions, from these normal distributions, it is then and very useful, very useful properties of the standard normal deviation, standard Gaussian distributions. It is the very useful, and it will actually used in real world. Okay, we'll see when we learn the some case study, when we discuss when some experiment using this algorithm, then we will see how much important these properties are. Actually, just simple using this formula, using these techniques, we can easily conclude that between the mean and the first deviations, our data sets are only accurate 34.1% of the data by using this only. Okay, and similarly by -2 and 0, or -2 and 0 means mean and first deviations only 34%. So our total, so on this range, so on the first minus sigma to sigma, our data sets are accurate only 68.2% of the data. 68.2% of that whole, on the whole data set, 61.2% of the data are accurate on this range, minus sigma to plus sigma. Or if you just consider this example that I have taken, then we can conclude that on -2 to +2 on these distributions, we have 68.2% of the data. This is the first thing. The second thing is that means on these regions we have 68.2% of the data. Now the second observation is that if we just increase the standard deviations, mean it is the first standard deviations, and 2 sigma, it is called the second standard deviation, and the 3 sigma, it is called the third standard deviation. Third standard deviations. So in the first standard, on the range of the first standard deviations, we have 68.2%, and on the third standard, on the second standard deviations, we have the 95% of the point. Means what? Means on the second standard deviations means 2 sigma, means minus 2 sigma to plus 2 sigma, we have 95% of the point. Let's see this thing now. Here we have 34.1%. Here we have 13.6%. Means how much? Means 34.1 plus 13.6 means 45. Here in these sides also we have 45%. So total we have 40. I think I am doing some mistake. So 34.1 plus 13.6. How much? The 6. This is the 7. The 47.7. And if you just 47.7, how much? 4, 5, 9. 95.4%. Is really simple. 95.4% data. So on this range that we have seen got, on this range we have 68.2% of the data. You just write clearly. On this range we have 68.2% of the data, and on this range, in this range we have, in this range we have how much point? 95.4% of the data. 94% on the data. So on this range we have, and anotherly we can call that on the mu and the second standard deviations, on the mean and the second standard deviations, we have its half point, means it's 47.7% of the point. Okay, and in the similarly we can, from here we can conclude that on the mean and the first standard deviations we have 34.1% of the point, 34.1% of the point we have. And on this range means mean and the second standard deviations we have 47.1%. And the similarly we can conclude that on the range of the third standard deviations, mean 3 sigma minus 3 sigma to 3 sigma, we have 99%, means also we have 2.1 we have to add. So 47.7 plus 2.1, 8, 49.8. If you just adding another 6, 9, 0, 0, 889, 8, 8, 9, 9, 99.6% point. 99.6% of the points are lying on this region. Or another language, we can conclude that between mean to third standard deviations we have 49.8 much number of points, 49.8% is number of points are lies between on these range. By simple, if you have a data sets and if you know the distributions of this data set, if you just know the simple distributions of these data sets, then we can easily draw this property, we can easily conclude this. We no need to calculate it each step by step, just you can using this property, and we will see these things how much it is important in the real world applications and how much it will be time saving in our calculations, how much it will take in time saving matter. Okay, that we will see in the next lectures. So now I think you have understood, I think you have understand these things. I think I'm taking the another examples to clarify these things more clearly. Okay, suppose let's take we have taken the height of a human. Suppose let's take we have anyone collected the data and we have find its distributions, and they have give us that our height of a humans and give the random variable height of a human x, and it's follow these distributions. Normal distributions with mean is equals to 150 and standard deviations is equals to 25. Okay, so here, so from here mean means mu is equals to 150 and its standard deviations is equals to 25. Just he gave these informations, and we don't know anything of our data set of our human height. Now using this formula we can conclude some beautiful property of our human height. How much humans are lie on this range of the height, how much humans are lies on this, how much humans are taller, how much humans are shorter, and such kind of things we can easily conclude that. Just see these things. So from here, just if you apply the first property, this first property here, these things, so we can conclude that on the first standard deviations means sigma standard deviations minus sigma to plus sigma, we have concluded that we have 68.2% of the human, 68.2% are of the humans are lies on this range. The height of the 68.2% humans are lies on this range, means how much this one will be plus if you here actually here we have mu is equals to 0, as in first case we have mu is equals to 0, so because of that we have this one, so it will be mu plus in every step, it will be mu plus also here mu plus mu plus, because in previous examples I have taken mu is equals to 0, but in generally it will be mu plus. Okay, so it will be mu plus. So mu plus, mu means 150, first mu minus or 25 means 125 to 175. So the height of the 80s, the height of a human, the height of a 68.2% of the humans, the height of the 68.2% of the humans are lies on this range, means 125 centimeter to 175 centimeters. Our humans height, means 68.2% humans heights are lies on 125 centimeter to 175 centimeter. This is the first observations. Now the second observations is means mu minus 2 sigma and mu plus 2 sigma. On this range we got that we have 95.4% of the data lie. Okay, this means what? This means 150 minus 2 sigma, 2 sigma means here 50, so in a range of the 100 to 2 sigma means 200. I think it will be 200, will be 95.4. So the 95.4% of the humans heights lies on the 100 centimeter to 200 centimeter. This is the second observations we can conclude. And the third observations we can conclude that mu minus 3 sigma to mu plus 3 sigma, on this range we have 99.6%. Means what? Means on this range 70 minus 25, okay, 75 to 225 lies of this. So 99.6% humans heights lies on the 75 centimeter to 225 centimeter. This is the actual observations from the, just I am taking that examples that that distributions will not be similar on every data set. Just for understanding purposes I am taking these examples. Okay, so I think you have understands. Just using these distributions we can conclude these things, how much important this formula is. That is that the simple, because of these reasons these formula are called the 60, 68, 95, 99 rules. If our distributions obeys the standard normal distributions, then we can easily conclude it. On the range of the first standard deviations we have 68.2% of the data. On the range of the second standard deviations we have the 95.4% of the data, and on the range of the third standard deviations we have the 99.6% of the data. Because of these reasons, is this technique, these rules are called the 68 to 95, 99% of 99 rule. I think you have understand the importance of the cumulative distribution functions, and using this cumulative distribution functions how we can conclude conclude some properties of our data sets without observing, without anything. Okay, and I think you have understand the importance of the 65, 68, 95, 99% rule and how much it is important. If anyone give a distributions that is obeys the standard normal distributions, and if it gives the two parameters that is mean and standard deviations, then we can draw these three properties. Means on the range of the first standard deviations, our the number of points lie on this range is 68.2%, and on the range of the second standard deviations the number of points are up 95.4% of the data, and on the range of the third standard deviations we have 99.6% of the data. Okay, I think you have understands from these lectures. Now we will see its implementations and its real life applications on the next lectures.